Master Faculty of Natural and Agricultural Science 2020 dari University of Pretoria. Bidang Dr. Eder Kikianty adalah analisis fungsional dan fungsi rel, khususnya pada bidang geometry of Banach spaces, semi-inner product spaces, sequence spaces, and product spaces, dan juga inequality theory dan integral approximation. Beliau telah menghasilkan atau menuliskan sekitar 30 makalah ilmiah dan bagian buku yang telah dipublikasikan dalam berbagai jurnal ilmiah. Beliau juga aktif dalam memberikan seminar atau presentasi di berbagai pertemuan ilmiah. Salah satunya pada tahun 2014 beliau juga memberikan presentasi di SNAMA saat itu di ITB. Baik, untuk menghemat waktu, saya persilakan Bu Eder Kikianty untuk menyampaikan presentasinya dengan judul Geometrical Constants of Morrey Spaces. Silakan.
Terima kasih Pak Denny atas introduction-nya ya. Selamat siang, di sini masih pagi, di Afrika Selatan masih jam 8 pagi. Selamat siang untuk rekan-rekan di Indonesia. Terima kasih untuk panitia sudah mengundang saya untuk presentasi hari ini. Saya mohon minta izin kepada para peserta, kemarin sudah minta izin ke panitia. Saya akan presentasi dalam bahasa Inggris. Not used to doing math in Indonesian anymore, so please excuse me. Mohon maaf. Okay, so I will share my screen. Okay, bisa dilihat ya screen-nya.
Iya Bu. Yeah.
Okay, ya terima kasih. Okay, so what I'm going to present today, Pak Denny has already mentioned the title of the presentation. It's called Geometrical Constants of Morrey Spaces. This is a joint work with Pak Hendra from ITB, Yoshihiro Sawano, currently at Chuo University. He was at Tokyo Metropolitan University. And my friend and colleague, Chris Schwanke from Lyon College in the United States, who will be joining me in Pretoria next year. So it's joint work with these three wonderful people, and the whole project started with let me see a question that is posed by Pak Hendra when I visited him a few years ago. So he was asking the following question: what is the sequence space analog of the Morrey spaces? So the question essentially is like, if you're talking about the P-Lebesgue integrable spaces, the sequence space analog would be the little LP spaces. So if you look at Morrey spaces function space, what is the sequence space analog of this space? Okay, so first of all, at that time when Pak Hendra asked me this question, I didn't know about Morrey spaces, so I have to learn what it is. So I have here the definition for us. So Morrey space is introduced in 1938 by C.B. Morrey. And the definition looks like this. So if you look at the literature of the Morrey spaces, there are many variations. This is perhaps one of the simpler ones. And typically, if you go to I went to a function space conference once, so a lot of people spoke about Morrey spaces. There's always confusion between who is P and who is Q and all of those things. So just beware that when you read the literature on Morrey spaces, this is usually a problem. Okay, so the Morrey spaces that I'm going to use today, the definition, is the following. So it's a Banach space with the following norm. So the way you construct a norm is the following. You take a function f. This is typically a locally integrable function. You take the absolute value, raise it to the power p, and then you take the integral mean value over the interval a minus r to a plus r. Okay, so there's this.
Sorry, yeah. I think it's freezing.
Freezing.
Yeah.
Let me see.
The slide.
Very strange. Is it working now or not?
Still
also
in.
No.
still in the first page. Still on the first page.
Okay, let me see what I can do here. How about I stop share and I reshare? Maybe that would work.
Yeah, I think now it's the definition of Morrey space.
Okay, great. Okay, so let me just continue. Thank you for the warning. Okay, so you take the integral mean value over this interval a minus r to a plus r. So as you can see here, the function that I take is a function on r, but you can actually do function from rd, any dimension. So we can think about this interval essentially as a ball centered at a with radius r, okay? And this 1 over 2r, remember I mentioned about integral mean value. So this is, you divide this with the Lebesgue measure in this instance is simply the length of the interval. Okay, and you raise this to the power 1 over p, and you multiply with this constant here, which is, again, the measure of the ball to the power 1 over q. So it requires a second parameter called q, and the condition for p and q, it must be greater or equal to 1, and p must be less than or equal to q. Okay, and here you take the supremum over all possible center and all possible radius. So this is essentially generalizing the bounded mean oscillation spaces. Okay, but not today is not the day to talk about that in details. What I'm going to mention is the following, that if P is incidentally equal to Q, you recover the P Lebesgue integrable spaces, so your usual LP spaces. Okay, so now the question of Pak Hendra, what is the sequence space analog of this? So let's think about how we get little LP from capital LP spaces. Well, you simply just use counting measure and your integral becomes a sum. So now we need a reasonable replacement for this ball centered at A with radius. So the way we do it is the following. We take our center to be an integer m, can be anything, any integer, and your radius is a non-negative integer. We use the symbol capital N, and then you create, like in the previous case, ball centered at m with radius capital N, but you're only taking the discrete points, in this case, the integer points. So and you create a set, right? So what is the measure of this set? Very simple, it's just the cardinality of the set. So you can just count how many of those, it should be 2n plus 1. And therefore, one can define the discrete Morrey spaces. Now it's a sequence space. Taking values in k can be r or c. And you see here the definition look very similar to what we saw earlier, only the integral changed to a sum. The ball changes to this set, and the rest is the same. You take this to the power p, power 1 over p, measure to the 1 over q. And you take again a supremum over all center and all radius. Okay, so of course, it's not too difficult to show that this is the Banach space, and when p is equal to q, you recover the little LP spaces. Hence, we use the notation little l, p, q. Okay, so the result of this research, this project with Pak Hendra and Chris, is published in 2018. And round about the same year, Yoshihiro Sawano, one of the experts in Morrey spaces, I believe is Pak Denny's advisor, calculated the James constant for the Morrey space to be 2. So he's interested in looking at what is the geometrical behavior of the Morrey space. And Pak Hendra then asked, okay, can we do the same thing? Let's calculate the James constant for the discrete Morrey space. The natural answer should be also 2, right? It should be the same answer with the Morrey space. But the better question right now is, what is the James constant? At the time, I just heard of it, so it was a natural time to learn about the James constant. What does it say, and what does it tell you about the space itself? So in this talk, what I will discuss are the following: what is James constant, and I will introduce another constant called von Neumann-Jordan constant, and I will discuss the properties that are associated to them. And I will briefly discuss these constants for discrete Morrey spaces. Throughout the talk, my X is always a Banach space, and I will use the notation S of X to denote the unit sphere. So that's the collection of all everything with normal.
Dari tadi pagi, sekarang ini dosen dari.
Okay, so speaking of unit sphere, let's look at the R2 with various norms. Okay, so we have our usual circle. This is the unit sphere of your little L2 norm. And in little L4, you get something like looks like this. Apparently, the technical term is squircle, so it's a mesh between a circle and a square. And for little L1 and little infinity, you get square. Well, different orientation for little L1, but doesn't really matter. If you just simply look at the shape, they're both squares. Okay, so geometry of Banach space is essentially asking these kind of questions. What is the shape of your unit sphere? Okay, so if you look at the L1 and L infinity, you can say that, okay, these two guys are not round, right? Because you have these segments on the unit sphere. Whereas L2 and L4, they are round. Also, another observation is that this squircle is not as round as the circle, right? So one question that you can ask is, what about the roundness of your unit sphere? Is it round? Is it not round? Or can you compare the roundness of these unit spheres? So for that, the geometrical notion is the convexity. That's the sort of the formal definition of it. So I will go through very quickly what the definition for these convexity notions are. Some literature also call it rotundity. They're essentially the same. Okay, so I will abbreviate with SC by strictly convex. So Banach space X is strictly convex if the following holds. You take 2 points on your unit sphere, not the same point. T is between 0 and 1, and then you create this. So we know what this is. This is basically the line segment excluding X and Y. And the line, if you measure the line segment, or all points on your line segment, the norm is less than 1. So if you think about it, what this means essentially is that the line segment lies inside the unit sphere, right? Meaning round. The unit sphere itself doesn't contain a line segment. Okay, a little bit more informative than strictly convex, also a stronger definition is what is called uniform convexity. So X is uniformly convex provided we have here the epsilon delta relationship of the definition. So you give for all epsilon, one can find delta such that the following holds. You take 2 points on your unit sphere, and they are epsilon away from each other. Then the midpoint is less than or equal to 1 minus delta. So this measures, depending on what your epsilon is, how far is the midpoint of your line segment goes inside the interior of the unit ball. Okay. So when P is between 1 and infinity, all the little LP spaces are uniformly convex. So as you saw earlier, some of the pictures, little L2 and little L4, they are uniformly convex spaces. But this doesn't recapture the idea of who's more convex than the other one, right? And this is where we already have some idea from this definition. There might be something to do with this delta, right? Because depending on what epsilon you feed into this definition, it might give you a certain delta. So this brings to the notion of modulus of convexity. So this gives you more quantitative information on the measure of roundness. This is a function from 0 to 2. So your epsilon, the lowest possible is 0, the same points. The highest possible is 2. This means that your points are antipodal, right? This goes to 0, 1. And this is defined as follows. You take the infimum over such possible x and y of the following, 1 minus norm of the midpoint. Right, so this definition essentially comes from what we saw earlier here. Right. Okay. There's also a constant that is related to this. If you take all modulus of convexity at epsilon equal to 0, and you take the sigma over all epsilon, this is called the characteristic of convexity. And using this information, you can characterize your space being strictly convex or not strictly convex, and so on and so forth, by the following. X is strictly convex if and only if the modulus of convexity evaluated at 2 is equal to 1. This means what? Means that only antipodal points of the unit sphere have distance equal to 2. obviously wrong for little L infinity. You can take 0.11 and 1 minus 1, and this is not true anymore. Okay, to characterize uniform convexity, your modulus of convexity must be positive for all epsilon positive less than or equal to 2. Or you can, you can also use the characteristic of convexity where it must be equal to 0. Okay, so now let's look at real quick, what is the modulus convexity of the LP spaces? So for P between 1 and 2, for any epsilon between 0 and 2, there's no nice form for your delta. You have to solve this equation right here. For P greater or equal to 2, it's quite nice. It's a closed form for this. It's 1 minus this quantity right here, which I'm not going to read. But anyways, this is quite nice because you can simply just choose P to be 2, for example, P equal to 4, and then you can compare these functions. I plot here P equals 2 is this reddish one, and P equals to 4 is this guy. Okay, so there's more quantitative information now on modulus of on the convexity. Okay, so speaking of convexity, why is it important? Okay, if your unit sphere is round or not round, why does it matter? Well, it matters for a number of reasons. So, for example, in approximation theory, you have in a Banach space, for example, if you take a convex subspace Y, and strictly convexity guarantees the uniqueness of a best approximation. If such approximation exists, both existence and uniqueness will be guaranteed if you change this to uniform convexity. The other importance is in fixed point theory. If you have K is a bounded, closed, and convex subspace of a uniformly convex Banach space, and you have T from K to K is not non-expansive. What does this mean? If you take 2 points in the domain, and you measure the distance between them, and you measure the distance between the images, then the distance of the images is not larger than the original. The word non-expansive is quite descriptive. The distance doesn't get bigger, yeah? Then T has a fixed point. Okay, so when talking about fixed point property, typically people try to either change the condition of the subspace or condition of the Banach space or the condition of the mapping. So it is going to come back in just a moment. And there are many more, but because of time, I'm not going to talk about everything. Okay, so the second geometrical property that I want to talk about is what is called the uniform non-squareness. So let's get back to the picture again. We mentioned that, okay, this is a square shape, but you can also say that, well, these two guys are not square, right? And again, we can observe that the circle is more non-square than the squircle. So now we need a notion to capture this idea and to capture this idea. And this definition is given by James in 1964. So X is called uniformly non-square if there exists delta between 0 and 1, such that for any points on the unit sphere, either norm of X plus Y over 2 is less than or equal to 1 minus delta, or X minus Y over 2 is less than or equal to 1 minus delta. Okay, so if you think about the negation of the statement, right, you will get a square. So for example, if you're in little L infinity, if you take point to be that one, then X plus Y over 2 is that guy over there, and the norm is 1. X minus Y over 2 is that guy over there, and the norm is equal to 1. So the negation of this is basically how you can identify square on your unit sphere. Okay, so that's the idea. And of course, this expression we saw already earlier, right? In a stronger form in uniform convexity. In fact, this uniform non-squareness is a weaker notion. So if you start with a uniformly convex space, you immediately get uniform non-squareness. Then of course, as mathematicians, if you have an implication, you always ask, well, what about the converse? Is this true or not? Well, I already did say it's a weaker notion, so it shouldn't be, but here's an example. This is given by Kato and Takahashi in 1997. So in your little L2, let's define a new norm. Take a maximum of the L2 norm and lambda times the infinity norm. Okay, so you take the maximum of this. This is a new norm. And with this new norm, your L2 is uniformly non-square, but not strictly convex, so not uniformly convex. Uniformly convex implies strictly convex. I perhaps have mentioned it earlier. If not, I'm sorry. Okay, so the converse of this statement is not true. This norm, however, has a nice picture. So if again you equip R2 with this norm, you get this picture right here. So just take your L2 sphere and your L infinity multiply with, I choose here lambda to be 1.25, and you take the minimum of it. So because this is, you're taking the unit sphere, so you must take the minimum instead of maximum, and you get this red shape. So it looks like a stop sign, but has some round shape there. Okay, whereas everywhere else you see that this cannot be strictly convex because there are line segments there. Okay, and what about the implication between uniform non-squareness and strictly convex? If you take in C01 the norm infinity plus norm 2, this is strictly convex but not uniformly non-square. So there's no implication between strict convexity and uniform non-squareness. So they're completely separate. Okay, you can characterize uniform non-squareness using the modulus of convexity. So here, notice it looks similar to what we had in uniform non-squareness. In uniform convexity was for all. Now it becomes for some. And the characteristics of convexity here needs only to be strictly less than 2. Also showing, again, this is a weaker notion. Okay, so the strict convexity and uniform convexity, I'm not going to explain too much about this. They're dual notions to smoothness and uniform smoothness. So for example, if your space is uniformly convex, then its dual space must be uniformly smooth. So the idea here for smoothness, just think about your unit sphere doesn't have sharp edges. Okay, I'm not going to give formal definition. What about uniform non-squareness? Takahashi and Kato in 1998 show that they are dual of each other. So if you have a space that is uniformly non-square, then the dual space is also uniformly non-square. So markedly different. And finally, not only uniformly convex space have the fixed point property. If you keep the sentence and you simply change the UC to UNSQ, the statement is still correct. This is proven in 2006. So if you only care about fixed point property, you don't have to go all the way to uniformly convex spaces. You can just simply stay at uniform non-square Banach space. So therefore, enlarge your choice of Banach space. Okay. Finally now, what is James constant? So I put there the definition of uniform non-squareness so that you can see where this James constant is coming from. Okay, so you take, because of this either or, right? You take the minimum of norm of x plus y and norm of x minus y. But you say, hold on, there's over 2 over there, but doesn't matter, you can just scale it, right? So you take the minimum of this and you take the supremum over all x, y in your unit sphere. And this is what James constant is. So the idea here is it's measuring non-squareness, right? So the question of how non-square is your Banach space. Okay, so you can, for any Banach space, show that the James constant of the space always greater or equal to √2, less than or equal to 2. It's equal to √2 if the space is Hilbert, but not only if. Counter example, just think of in R2 with your unit sphere being a regular octagon that is not uniformly, that's not Hilbert, but is uniform non-squareness with √2, with constant √2. Okay, and if your dimension of the space is greater or equal to 3, you get if and only if. You can characterize uniform non-squareness now using the James constant if it's strictly less than 2. Okay. And for LP spaces, it's a quite nice form. It's very simple. You just take the maximum of this depending on your P, obviously. So you can look at, for L2 is √2, for L4 is 2 to the power 3 over 4. So you can again give a quantitative information on this. For L1 and L infinity, the constant is equal to 2. So it is the upper bound right here. Okay. All right. So one more constant. This is very easy to explain. Von Neumann-Jordan constant arises from the idea of parallelogram law. So we know this from our linear algebra courses. And we know that X is a Hilbert space if and only if, well, inner product space, if and only if it satisfies the parallelogram law. So the idea of von Neumann-Jordan constant, now we want to measure how close is your norm to satisfy the parallelogram law. So what you do is just divide this guy with your right-hand side, take the supremum over now all non-zero x and y. Okay, and this is called the von Neumann-Jordan constant. So for any Banach space, again, one can calculate that the von Neumann-Jordan constant is always less than or equal to 2 or greater or equal to 1. obviously you can already see if it's a Hilbert space, then the von Neumann-Jordan constant must be equal to 1. In fact, this is if and only if because of that statement above. So over here, you're very close to Hilbert space, right? If you're closer to 1. If X is uniformly convex, then the von Neumann-Jordan constant is strictly less than 2. The converse is not true by the following statement, because this von Neumann-Jordan constant less than 2 characterizes the uniform non-squareness. And again, for LP, there's a nice form. And you can simply calculate for little L2. Obviously, it's 1 because it's a Hilbert space. The L4, you get root 2. L1 and L infinity, you get 2. So if you're close to 1, you're more close to Hilbert space than if you are close to 2. This is the as worst as possible, if you like. Okay, so bringing all of this together to your Morrey space, I mentioned earlier, Yoshihiro has calculated for Morrey space, the constant is 2. So it's pretty bad. It looks like L infinity, right? These spaces are not very nice. They're very far away from Hilbert space. And we joined forces with Yoshihiro, and we managed to also prove a similar thing for the discrete Morrey space. And in my next few minutes, I'm going to try and explain how did we get to this conclusion. Okay, so first of all, LPQ is a Banach space. So you know that the constants, whether James or von Neumann-Jordan, is always less than or equal to 2. So if we want equality here, all we need to show is to find 2 vectors that making that supremum attain at 2. That's essentially the idea. Okay, so I'm going to leave this sentence as is. You don't have to worry about that awkward number. It will make sense in just a moment. Okay, so first you take 2 sequences. The first one, x at 0 is 1. At n, for some n like that, is 1. Everything else is 0. For y is similar. At 0 is 1. At n is -1. And everything else is 0. Then you simply plug into your formula of discrete Morrey norm. You get this nice expression here. I spare you from the awkward calculations, pretty long. It's about half a page. Anyways, and so the idea here, I want my x to be in the unit sphere, right? So basically what I'm doing is I want this guy to be less than 1. So when I take the maximum, I get 1, right? So I simply just make this less than 1 and solve. And this is where that choice of n coming from. Okay, that's the idea. So now your x is in the unit sphere of little LPQ, okay? And a similar calculation, you can also show that this y is also in the unit sphere, okay? So now we're in business. We get an x in the unit sphere, y in the unit sphere. Now let's count our norm of x plus y. You get 2. Norm of x minus y, you get 2. So you take the supremum of this guy, you get 2. So the James constant is equal to 2. And similarly, if you look at, remember this is 2. So 2 squared is 4, plus 2 squared is 4. So that's 8. Over here we have what? 1 plus 1 is 2, times 2 is 4, times 2 is 8, right? So it looks like your parallelogram identity, except there's an extra 2 here. So when you divide with the right-hand side, which is that guy, you get 2. So the von Neumann-Jordan constant for this discrete Morrey space is also 2. So they also behave like very ugly, like the L infinity spaces. Okay, so that's all I would like to say for today. Thank you very much for your attention.
Thank you. Terima kasih Bu Eder. Any question? Ada pertanyaan? Baik, jika belum sambil menunggu, mungkin saya memberikan pertanyaan dulu, Bu. Is it possible to use the connection between discrete Morrey space and Morrey space in your paper, I think, with Christopher? Use the result of the geometry of Morrey space to translate it to discrete Morrey space. Is it possible?
Oh, you mean because it's a closed subspace?
Yes.
Yeah, okay. I honestly haven't thought of that yet, but I think with geometry, one has to be careful because this idea of taking a subspace may actually change the shape of your unit sphere. If you just think about some random in R3, right? Whatever your unit, your polyhedra looks like, it depends on where you slice it, right? Let's say you try to find a 2-dimensional subspace. Depending on how you slice it, the shape might be different, right? So maybe in one shape you get a circular, maybe in one shape you get an octagon. It depends on the it can be very ugly. So that just I think intuitively, I think that might be my answer. Yeah. So you can't really say the geometry being taken so quickly just because something is a subspace of another thing. So it depends on the situation, I think.
Yeah. Also the size probably.
Yeah, or the size, or maybe how
subspace.
the uniformity of the how does it behave. This idea of slicing, I think, is probably the way to think about it. Yeah.
Thank you.
Yeah.
Any other question? Comment, please. Pak Hendra, terlihat di layar. Oke. Yeah.
You wrote the paper.
Oh, okay. Pak Oki? Okay. Okay, I think, yeah. Okay, there is a question from Pak Eri Dani.
Ada Pak di chat Pak.
Yeah, Pak Yudi and Pak Eri Dani. I will read the question. Just wondering what kind of information the facts you establish in this Morrey space fit back to continuous Morrey space. One question from Pak Yudi.
Yeah, I have to think carefully here. It might not actually have a lot of so to say feedback, because if you think about they behave similarly in a sense, but they also behave differently in another sense. Because if you think about continuous Morrey space, well, what I show is using Lebesgue measure, but of course you can use different measure maybe for. I'm not sure, Pak Hendra, if a different measure is given for generalized Morrey space. But anyways, but if you look at the discrete Morrey space, you use counting measure, and this is a non-atomic measure, right? So I don't think they behave similarly in a sense, but they also behave differently in another sense. So one can actually look at this as a separate space. Yeah. So I'm not sure if there's a feedback, but maybe there is. I'm not entirely certain.
Thank you. I will read the next question from Pak Ridani. Ruang barisan Morrey yang paling sederhana bisa jadi indeksnya mulai dari 1, 2, 3 dan seterusnya. Bagaimana jadinya dengan konstanta tersebut? Mungkin kalau
ya, kalau dilihat kenapa kita pakai Z, ya, itu supaya lebih gampang dalam expressing the idea of the unit of this ball, right? Center at A, radius R. So A minus R to A plus R, that kind of idea. Kalau hanya dari 1, 2, 3 dan seterusnya, well, this can be an issue, right? If you start your center at 2 and your R is minus 2, then you have a problem. Sorry, your R is 2, then you have a problem. Jadi, if you want to sort of, you can shift this, right? This is not a problem. You can basically change from Z to N just by simply changing the index. I don't think it will change any of the constant. It will still be exactly the same space, I think. Yeah, the reason of choosing Z is actually for the reason for that ball to make sense, so to say. Yeah.
Baik, terima kasih Bu Eder. Thank you. I think it's a very interesting topic here. Thank you. Terima kasih sekali lagi Bu Eder Kikianty untuk bergabung di SNAMA ini. Terima kasih. Untuk berikutnya saya kembalikan ke pembawa acara. Terima kasih.